Yeah. So there is one at the bottom. Try your luck. Right. So let's start today's session. Thank you everyone for showing up. Again, my name is Mohsin Sheikh. I am one of the computational scientists at KAUST Supercomputing Lab. With me today are Dr. Didier and Dr. Halimi. They are from KAUST Visualization Lab, and together we take care of the data science aspect of our platforms. Today, we are talking about increasing the throughput of hyperparameter optimization for ML and DL workloads. Now, this is more focused towards deep learning, but the techniques that I'm going, or the library that I'm going to talk about is going to serve you well in the machine learning aspect as well. So scikit-learn. I mean, you can use the same algorithms for that front. All right, so how we move in today's session is, I'm not sure how long is it going to take. It's definitely not 3 hours of auto material, but I'll try to consolidate it as much as possible. So first we'll look at why do hyperparameter optimization, and then we look at a library called RayTune, introduce ourselves with it. We go through a few demos, and we'll basically go through demos after that with due intervals. You are welcome to join me. I probably have not shared the GitHub repository with you, but I'll put that on the screen in just a second. You can clone that repository and get your hands dirty with it. Then we are going to talk about, okay, fine, we have a framework. Are there any search algorithms that we can use to find a good, best fitting parameters? And then are there any prerequisites for that? And at the end, I'm just going to do an honorable mention of weights and biases. This is a cloud-based platform. How many of you use it day in, day out? Okay, at least one. So this is something where you want to collaborate and share, or maybe archive outside KAUST your experimentation. By versioning the experimentation from a model, from a data point of view, and from infrastructure point of view. I'm talking about the software infrastructure as well. What did I run? How much did I run? And what were the parameters and the metadata of it? Okay, so enough said. What is a hyperparameter? Okay, by definition, the hyperparameters are not the model parameters. That's number one. They are the ones that you set before you start training the model. So you don't change it during the model training itself. It is an optimization problem to find the best mix of these hyperparameters. So you set them ab initio, run the whole thing, and then see the metric, and then go back and change it accordingly. The best combination is sensitive to dataset and the model used for training. So complexity of the model and the dataset itself can determine the best combination and search for it. How hard will it be? So what is the usual pattern, how one would think? So you have a first draft of the model, version 0.1, and you have your representative data set. You pick a candidate parameter and set values. You may want to set ranges, strides, or random sampling on that selection. You then train the model with a combination. Let's call it a trial during your experiment. Then compare the results with the previous trial, and then pick the best performing trial between the two, and then basically go back to one until the parameters are exhausted, the ranges are exhausted, or you'll hit the accuracy or a loss that is acceptable, right? So that's where you kind of stop. So this is a general pattern that one would think about in a workflow that can take at least days, if not months or years, depending on how much resource you have. And then that can easily become like few jobs to few hundred jobs. I will be highly surprised if I really sat with every user of IBEX and then requested them to explain their work, and it was not hyperparameter optimization. So imagine how much we can reduce if there is an intelligent way of finding those. Why use a search algorithm? Well, as I mentioned, intelligence. Why use intelligence there? The models are sometimes complex. So the search spaces of these hyperparameters can be large, and they can be complex as well. Brute force, when you basically do a grid search, for example, can be very expensive, both in time and in money, especially when you're doing things in cloud, for example. Here, you don't care, but you might start caring, because I know a few principal investigators, professors who actually invest quite a lot of money in cloud to increase the resource that they have access to. And that is a lot of money. And scarcity of resource may also limit the optimization space. So at the end of the day, you may call it a day after the 10th trial, saying, okay, fine, I'll just guesstimate it from there on, and then this is my best, and then let's publish. So essentially, you never exploited the whole parameter space. Common methods or common search algorithms are manual search, grid search, random search. In scikit-learn, you might have come across random forest. And then it becomes a little bit sophisticated depending on how much statistics is involved in there. Bayesian optimization or sequential model-based optimization, genetic algorithm, asynchronous successive halving algorithm, hyperband, or population-based training. So we are going to mention the last one a little bit, what that is, but there are quite a lot of them. There are quite a few, actually. And it would be worthwhile to just start easy and then ramp up on more complex ones. They can aid in both speed and in quality of the metric combination, best metric combination. So let me switch to the library itself. Basically, what I want to talk about is RayTune. Ray is a general framework which comes as Ray Core. And then there is a library plugin for it for tuning hyperparameters. It's called RayTune. So with Ray, you can do much more than hyperparameter optimization. You can, it is a way of distributing, right? And it supports quite a lot of platforms. Cloud native, Kubernetes, schedulers like Slurm, for example, your laptop, and so on and so forth. But then there are special topics like tuning, reinforcement learning, and if I remember correctly, they have their own SGD for PyTorch and TensorFlow, so on and so forth. I mean, there are more than one plugins, so have a look at Ray in general, but we're talking about RayTune. So what is radio? It's a library to scale hyperparameters, hyperparameter tuning, with distributed trials over CPUs and GPUs. So each trial can actually be considered as an exclusive event, right? If it is an exclusive event, why do I need to wait until I finish the first one, right? Why can't I run them concurrently? That's the idea, right? And if I start sampling the available space, I could find that there is information in the first bunch of trials that I can use to pick and choose the next bunch. So I can be moving through the space intelligently. So what it does is it allows you to use multiple devices and multiple nodes, right? When I say multiple devices, it can be CPUs or GPUs, and then multiple nodes, multiple machines. It supports PyTorch, TensorFlow, Keras, XGBoost, scikit-learn, and I have seen the PyTorch, excuse me, PyTorch Lightning integration as well. Okay. It has in good integration of baked in search and scheduling algorithms, population-based training, Bayesian optimization, hyperband are a few honorable mentions here. You can bring your own as well. So if you know and love something that you are familiar with, you can bring, let's say, Optuna, Hyperopt, Nevergrad, and so on and so forth. I'm not very familiar with these, but yeah, you can bring your own. Optuna is very popular, by the way, that I have seen people using. Okay, how does it work? So Tune gives you an API, an application programming interface, where you basically it's called a trainable API. And this API can be exhibited in your code as a function or as a class. Okay. And then basically in the class, you inherit from a parent class. And then you configure, you set the config dictionary that it takes in, and set some things in there, including your hyperparameters. Mention your hyperparameters there and the search spaces, how you traverse through the search spaces, the scheduler, the early stopping mechanism, if there is possibility, and so on and so forth. So this is kind of a setting up of the experiment within a framework. So trainable API is the framework. You set the framework in the config dictionary, okay? Optionally, you set the search algorithm and the scheduling along with it, including checkpointing mechanism. So basically, how do you want to organize the checkpointing? Because remember, these are there is a element of benefit in checkpointing in two ways. One is the continuity part, when things finish before they, when resource allocation finishes before the actual experiment has finished, you're still left with a lot of trials, you can resume that. Or you can checkpoint and then restart from a better model, a better performing model. So you need to basically capture that too. Once you have a trainable API set up, then you pass it to the, you call the run method on that trainable API, and it runs. It runs the search algorithm and the trial scheduling as well. So depending on the search algorithm, it will schedule the trials accordingly based on the resources. Once it is done, it also gives you a method of analyzing your results in whatever way you want. When I say whatever way, within the constraints of whatever it can do, but generally speaking, best configuration, best trial, best metric, and so on and so forth. So I'll be exemplifying very basic stuff of what you can do, but you can dive in more into the analysis part of what can be achieved. Generally, I mean, we are concerned with the best combination. Okay. As I mentioned, executing the experiment is calling tune.run, and analyzing is analyzing is when tune.run runs, it returns back an object, and then you can analyze that with best trial configure results. So let's dive into the demos. What I'm planning to do is run a hello world a program for optimizing an objective function. A very simple example, has nothing to do with MLDL, but it's just an objective function that I want to optimize to maximize the value or result. The next one will be MNIST training, finding best parameters for that to give the best accuracy. And the last one, last two are to do with the scheduling, and then how do you integrate it with weights and biases API. So for the hello world, what we have is a function that we want to maximize the value of, and here A and B are the parameters. So we will keep on changing the values of A and B until we find the best parameter. So let's have a look at the code. In the code, we'll be first looking at the script, and then we'll be looking at the job scripts that allows us to orchestrate a array cluster on IBEX and run our tune experiment. Okie dokie. So what I have is this visible, or should I blow it up? How about now? Better? Okay. I don't like this. How do I get rid of that? Here we go. Backup. So HPO training. Okay, so first things first, I need to give you the GitHub repository. So if you want to follow me, please do. Git remote show origin. Okay, so this is it. You can either copy or write it from here, or you can find me on GitHub and then look for this repository. Say it again. msheikh786. How's that? So at some point, I'll move it to our KRCCL. Actually, I can do one better.
They just write git and the link. That's it.
Git clone.
Git clone.
Yeah. I think you should receive this email as well. While we are doing that, yeah. You cloned it? In the what? Oh. Be ready for the trouble. Okay. Right. So server. So one bad practice. Hey, come on. One bad practice that I have done in all the job scripts, I have the account. Please comment that from all the job scripts. That is my account. So it won't work for you. So in the job scripts, this is ibex.cs or ibex-cs. Just comment that part and it should work the rest of it. And it has no 800 in it. So when it's general lightweight stuff. So first things first, I need to. So this is how it looks like. I am going to run a server. I'll explain it in a bit, what a server and a client means. But let me do that. And then I switch client.
So we can solve your content environment. Okay. It has the line source, activate way to.
You can't. That too, that you need to change that too. So once you create a conda environment, you source your own conda environment. This is just a placeholder. Not for this training. We don't have Ray installed in that. We do? Which version do we have? If we have it, then try it.
Yeah, I can promise it will work because I don't know which version.
Yeah. I'm doing the latest bit, 2.2. So I'm sure it's most of my code is backwards compatible. Actually, it is based off of 1.3. 1.13, sorry. Yeah. 2.1. Okay. Yeah, you could use that too. Yeah. Do you have 1B?
Yeah, 1B.
1B.
Yeah, we can buy it.
Yeah. Cool. So it's mostly there, everything. So why I add the conda environments is basically if you don't need anything else that is already there in modules, use the module. That's perfect. But if you want to update or change the environment, you may need to create conda environments. Okay. So less on Ray client. And here I should have, where is the SSH command? SSH, here we go. But it's too big for my screen. That, I'm just doing a demo. If you want to follow, you can. Otherwise, I'll just explain what the things look like mostly.
But to create the content environment is the file,
it's in the conda directory of your GitHub repository. And instead of using conda and create, try using Mamba. If you don't have Mamba installed, install it in your base directory, base environment. Conda install Mamba, and then Mamba is a tool which does a parallel build of all the environment. Okay, go here, here, and this. Right. Okay, so the first thing first that we do is basically we import Ray and we import Tune from it. Those are the two major libraries. Then we read some information. So how it works is Ray is going to start a cluster, and the cluster will have a master and workers. Okay. So what we just did was I submitted a job called server.slurm, and server started the master part. Now the master is running on a CPU resource, not on a GPU. So it doesn't require GPU, right? So it is running on a CPU resource. It is starting with an IP address and a port, and then it is ready to be connected to by the workers. Now, worker is a separate job, separate Slurm job. And in this scenario, it's a Jupyter job, right? So it starts a worker and with the information of who am I going to connect to, right? So that's exactly what this cell is doing. It is reading from a file that the server has dumped. This file has been created by the server. It has very little information of which IP address the server is running on, which machine the server is running on, and which port should I be communicating on, okay? And the server also runs something called a Redis database. It's just a database, but it is password protected database, okay? So if all of us are running on the same node, a server of Ray, everyone's job will start a database of their own, but we cannot connect to each other's because it is password protected. So the password is also in there in that file. So that's what I'm doing here. I'm actually splitting the output and then reading the address and the password. So here I go. I did that. And then this is to connect my worker. So each entity in Ray must call this, okay? So that it can connect to, register to this master. Why is it important? Because you must have understood that already, but the master is running a database. Database of what? Database of tasks. It's a journal. And the workers will be there as a resource. Now, what is the master going to do? It's going to give tasks to different workers to do. In this case, it's going to give trials to run on different workers, okay? So that's what the intent is. Surprise, surprise, it went flawlessly and then connected. Now it is telling which Python version is being used, what version of Ray is being used, and there is a dashboard. So you from here, you can actually start a dashboard. Don't rely too much on this dashboard because it is looking at the whole machine rather than the job itself. So I really rely on that part. Okay, now the meat of the matter. Our objective function, remember, we had a and a B parameter, and we were solving this equation. And it's a simple definition of the function. So let's define that. Now we wrap this into a trainable API. Remember, we spoke about this just a while ago, that it requires us to express our workload. The tune library requires us to express our workload in an API. You can call it as a function or call it as a class. Here, I'm calling it as a function with a dictionary of configuration, right? That config dictionary, when tune calls it, will pass that dictionary to trainable function, right? And I'm basically expanding the dictionary to retrieve the parameters that were set for the trial. And then I run those basically and then solve it 20 times until I reach the 20th iteration. And there will be a value, a result, the left-hand side. I want to capture it as my collection metric, right? That's my score. I'm returning that to tune.report. So that's a metric collector for the tune so that it can capture that result. And then this result, excuse me, will be coming from different workers, and it will be registered and decisions by the master will be made on that. Okay. All right. That is defined. Now it's time to run. So we call the method tune.run with the trainable function passed. We set the number of samples. So how many total trials are we supposed to run? we set the stop condition. So what is the maximum the trial should run to? I am setting a stop condition on a monotonically increasing metric. That's the training iteration. So on 20th iteration, I want things to stop for every trial. And whatever the score is, please get that score from there. I'm also setting the resource per trial. So I want one CPU, maximum of one CPU to run each trial, okay? So if I start with 4 CPUs, and if I have 20 trials, there'll be a register, and all 4 CPUs will be busy until the trials are exhausted, okay? I set the configuration of A and B, my parameters. It's 0 to 20. That's like a linear space because it's a uniform distribution between 0 and 20. And how many maximum trials should run at the same time? I'm saying 8, for example. I might not have enough resource, but I may have more resource as well. So this is a parameter to tune how much workload do I need to spill through before running this. This may actually be consequential because you are increasing or decreasing the sample concurrently running, and then if you're using an intelligent scheduler, that may have a better understanding of the first batch of experiments that it is of the trials that it is running. So let's run it. So it's going to go and schedule the resources. So you can see that it has deciphered how many resources did we ask for. If I go back to my job script for a second and look at the client job script, for example, I had asked for 4 CPUs from here, right? And funny enough, I had also asked for some CPUs here, right? So there were 2 here and 4 there. In total, it is looking at all 6 of them and using it as its resource. And then as it goes along, it is basically creating a excuse me, truth table for me about the true and the false. And as you can see, the state of it is there, the experiment ID is there, the iterations are there, and the score is there as well, right? So I'm trying to maximize my score, and let's see how I can deal with the best fit. But there is quite a lot of metric about every trial that I ran, right? Even the state of it is there too, if you want to follow that. So at the moment, I think the cell is finished. Yes, finished. And then I print the best configuration of the matrix score, depending on the matrix score, with the mode max, which basically means I'm trying to maximize it.
How do you calculate the score?
How do I calculate the score?
Based on what you find?
That the left-hand side of this is my score. That's the, all right. So this could easily be the accuracy or a loss function, output of the loss function. Okay, let's do that. Let's see. Okay, so it gives me A and B values of this experiment, the best of this experiment, where the score was best. I could retrieve what's the best trial. So it gives me the trial ID there. I can go and have a look at that directory. By the way, I can pass on quite a lot of things, including the log directories, where I want to put the log of each trial so they can be accessed later. Okay. So this was how you manifest your trainable API as a function. Let's have a look at the class. And I mean, it depends on you as a software developer, how you want to take up and include it in your code. So exactly the same thing that we were doing. The first 2 cells are absolutely the same. And then we connect. Yes, we have connected. The objective functions remain the same. That's perfectly fine. Now we define a class and we inherit from tune.trainable. That's the parent class. And in that, we define our X, A, and B as we were defining. And then we define the step function. In the step function, as before in the function train.api, we were wrapping it. Here we wrap the score function, the objective function as well, and then get the score, increase the parameter, and then return the score as the metric. There's nothing special happening here. It's just the same implementation, but as a class. Okay. So Tune is intelligent enough to decipher between a function and a class. And at the end of the day, it's a Python object to it. And then we do exactly the same as we did before. Okay. And then because the stuff is going to be a bit random, one thing that I have seen is that there may be performance difference running a class versus a function, depending on how heavy the computation is. Yes.
When you calculate error, you calculate what?
Are you talking about score or error?
Yeah.
Error of what?
Function a square root of
Yeah.
x plus b, right? And we want to keep this function, right? Somewhere.
We want to rerun this function with different values of a and b.
We want what?
Rerun this function 20 times or 200 times with different values or different combinations of a and b. So those are our
Find the optimal
maximum value of score. Yeah.
Score.
Yeah.
Relative to which
okay, so relative to which true? Well, relative to the all the values of the trial. So it is going to run two combinations, and then it is going to have a result, a score, and then you have a tabular data.
A and B function depending on A and B.
Yes.
And we compare this value with what?
We compare this value with other trials value. If you have 100 trials, we get a max out of it.
I don't get this because it's all of it.
Sure.
So okay, and purpose of it is to actually iterate over hyperparameters. So when you manually do hyperparameter tuning, you train the model, see what the validation accuracy, and then you get some metrics like testing, and then you think, oh, maybe I should have chosen another learning rate, or maybe I should have added more layers to the model.
Yeah.
These are all hyperparameters. And this is very tedious task to actually serve. Yeah, I think we have to measure finding the overall model. Yeah, and this this training cycle and its validation score is a black box, so to say. So you can't plug gradients through the training process. So OpenML, they are pretty much they are guessing which is the next sample actually to try. And hope to find the maximum of the validation score, which is just a black box function.
So each trial in that scenario, and I think I understand what you're trying to say. So basically, we have to decipher two things here. One is the computation within the trial, right? And then there is a computation across the trials, right? Every trial is a computation, right? Every trial is an exclusive computation. So you will compare trial versus trial. So there will be a matrix that will be coming out of each trial, right? In this scenario, it's a score. It's a left-hand side of an equation, okay? But in the other scenario, in the machine learning and deep learning scenario, it will be loss function. Within the trial, you will have a ground truth, right? You already have that as one single thing, right? That remains as is, right? It will give you the answer based on the hyperparameters that you have fed to the training in the beginning, ab initio of that trial. So the A and the B, the learning rate and the momentum or something like that, we'll do that with MNIST right now. That is a single trial, and there is a reference point to that. We have passed the labels there, right? And that's where the error of that trial is being calculated. What will be reported at the end and fed back to this chart is the loss on, let's say, the 80th iteration. So every single trial will run up to 80th. That's the first stopping condition. But then you can actually terminate a trial if a trial is doing very, very bad. So for example, you can say, I'll explain in a second. For example, you can say, if I am on 5th iteration and the loss function is already 10 times more than it should be, please stop that trial. That's a bad trial. Don't run it to 80. So in that scenario, it will already curtail and then put it into a chart and then say, please don't consider that. That was terminated. That was a failure already. So, okay. So only consider the good ones. So as I mentioned, the error question that you asked was a trial specific thing. It's your logic, how you want to manage that.
A and B are different.
Absolutely. Yeah. All right. So, I mean, I tried to choose something very, very basic here so that the infrastructure is clear, and then we get into the real part. Okay, moving on. So that was the interactive way of running it, but let's have a look at the batch. So again, we have two Slurm scripts here. One is for the head node and the other one is for worker node, right? Now, let's look at the hello world. This is the Python script that encapsulate exactly what we saw in the notebook. There's nothing special happening here. Okay, except that I have a arg parser, which I can deal with from a command line. Nothing special happening there. So let's have a look at the head node Slurm job script. And this is IBEX specific, by the way. So you set what you want, right? You get your environment set. I am allowing myself to have more than one workers if I wanted to, but the default is one worker, and I'll tell you where this is being used. I'm setting some ports, and I'm starting the Ray server, okay? The Ray command with start, if there is -- head in the option, is considered as the server or the master, okay? I'm passing a few things here to it. The node IP address. What is the IP address of this node? What is the port it is supposed to use? And what Redis password it is supposed to accept when it is accepting the authentication of a worker. I can optionally start the dashboard. And here I can set the resources that the server can contribute. So -- num CPUs is going to be added to the available resource for the experiment, okay, from the server side, if I want to run the experiment on the server itself, right, including the workers. So that's You can choose not to. All right. And then I am going to submit the worker jobs, right? However, how many worker jobs? Well, the number of num workers will decide how many jobs are supposed to be submitted. And it is going to submit this worker underscore node dot slurm job script. All right. It's going to sleep for a few seconds until everything is awake and running. It's going to check and print out some status of the cluster, Ray cluster, when it is established, the server and the workers. And then it will invoke the workload. Now, this workload, understand that it is running on the server, because the server is supposed to read all that Pythonic logic and then break it down into tasks through that tune API. That's how we are orchestrating our cluster of tasks, basically. And then this is a shutdown routine where I am shutting down the server and then writing up a file which is going to be read by the worker. Here again, the worker allocation can actually be configured at your disposal, however many CPUs and GPUs you want in it, and whatever time you want in it. And the infrastructure is going to be read by a worker from this file. This file is being written by the server itself, okay? So you cannot write this file anywhere where the workers cannot access, okay? This can be the local storage or the file system which is not mounted on the worker nodes, okay? So say, for example, as you may already know, that Scratch file system is not mounted on 100 nodes, okay? So you cannot write this file and expect it to be read by the worker nodes which are running on 100, for example, right? Then you start the same way you started the server. You start the worker without minus head. Okay, so this is not a server anymore to Ray, it is a worker. And it is going to read the server's IP address and the Redis password and then try to connect to it. All right. And then it is going to wait until it is given all the work. Once the work is finished, it is going to loop on this existence of this file, shutdown.txt. If it exists, it's going to go and shut down itself, call a Ray stop on itself. That means the job will be finished there and the server job will then be finished. So let's have a look how it runs. Let me clean it up a little bit. Yep. And head node. So you don't have to remove this. It will be overwritten. So first, actually not first, just submit this and it will submit the worker jobs on its own. Oops, sorry. What did I do there? Twice? Why twice? So look. Okay, yeah, fine. I think this is, yeah, we need to cancel this and cancel this. These are from the Jupyter session. So let's have a look at the output of the head node. The head node is pretty expressive. When it starts the server, it gives you a lot of information. Excuse me. And this information is useful. We are already doing that, and it is giving you some information on what kind of Ray init you are supposed to run in your Python script. It's already there in our Python script, so we don't care too much. And then it is waiting for the workers to start. So let's have a look at the queue. Okay, so the worker job has started as well. So let's look at the worker output. It is trying to connect to the server, and it has connected to the server because I can see the number of CPUs here, total number of CPUs here. How did it become 12? Well, head node asked for 4 CPUs, right? And worker was submitted with a request of 8 CPUs. So there are 12 CPUs in total. Okay. Now, since head node is going to run the Python script, I should expect the output of my experiment to come in the head node's output, right, file. And this is what it is. Basically, it is trying to set different values of A and B, trying to run these experiment, this experiment, and you can see the allocation being used here too. 11 out of 12 CPUs are in business at the moment, with some memory being used, and so on and so forth, and a status of the trials. Okay, so I think let it run. So it is terminated, and the best configuration is out of maximum, I think 100 trials were on. And as I mentioned before, you can query more, and it gives you a little bit more statistics on the performance of the experiment as well. So you can decide on the requirement of your workload. One interesting thing that could happen is you may start with less resource and then, or more resource. If you can start with less resource and then want to add more resource. So there is an element of elasticity as well. So let's say if you had set the number of samples to 200, and the maximum concurrent runs are set to 40 already, but you only had 12 CPUs, right? So you still have a huge headroom of concurrency, right? You could do that you can start with, let me clean it up a little bit first. So I'm starting with 1 num workers equals 1. And I want to do is I want the worker to start first and the experiment to run. But during the experiment, I will start a new worker job, add another worker with 8 more CPUs. And my expectation is before they were 12, after the addition, they should be 20, and my experiment should run a little faster, right? So here we go. Cat on the head node. It is still waiting for the workers. Let's see. Okay. Starts with 12 with the amount of memory and so on and so forth. Okay, head, still waiting. Still waiting. Here we go. Some activity there. Okay, trials have been executing. So let's submit another worker, right? So you can actually do a standalone job of worker as well. Expectation is that it will read the same file, will try to connect to the same server that is already in place, and we should be able to see some increase in the resource. So let's see how it goes. Okay, so yes, The resource has increased to 20. And you can expand it or shrink it as well. So if I killed one of the jobs because it was an overkill, for example, or I had started with a maximum concurrent of, let's say, 15, I would then say, okay, fine, I have started a worker which is adding more cores, but they cannot be used because I have put a restriction on it. All right. So this was just a demo. Yes.
Okay, so why do they want to go for all the resources they can do? Like, can they launch like
Several jobs?
several jobs to reach 1,024 CPUs?
Technically, yes.
Or they will find themselves like in the queue, right?
Oh, yes. So then you will be in contention with others. And there is a top limit of however many CPUs you can use as a single user. So you will hit either that or you will hit a waiting time on some of the jobs, which is fine in a certain scenario, but not fine always.
Yeah, no. The question goes along the time. Like if the head node dies, then the worker node doesn't know what to do.
The worker node does know what to do. Basically, it will, let's have a look at the, so it will read this, try to connect this, and there are certain retries it will do. And then it will call, yeah. And then this is also a safeguard. So my understanding is that it will cleanly drive. But we are open to suggestions. Let me get some water. So think of any questions, please. If you have any for now, then we move to a deep learning example. Right?
Well, everything has been in CPU, right?
Hmm?
So far, all the samples that we have
Yes.
seen are CPU based.
Yes, yes. Now we are going to get into the GPU. Right?
In theory, they can run this in percent, right?
In theory, yes. I am curating the script system. Yes, please.
Way in the job queues. Any difference is there or I'm familiar with that one.
Job queue is there. It's a good library. I'm not familiar with the amount of intelligence it has and the integration with GPUs. I'm not sure about that. The other thing is Raytune is familiar with deep learning and machine learning workloads. So the manifestation is pretty much, around that workload. You can do anything and then express your problem in that way as well, and then use Tune for that. But yeah, there are several actually. This is just one. Let's go to the second demo. And before that, I have to go back to my slides. Okay. So we went through our first hello world pass. Now you can checkpoint your models, and your models can sit with different file names and in different directories. For that, you need to set the checkpointing true. I think it is true by default in the config of tune.run. You need to give a log directory. By default, it goes to home directory, but I would highly recommend putting it into the Vecca file system, where you can have both capacity and IOPS while setting up that directory. Because remember, we just did n samples equals 200. So there'll be 200 trials running. It could easily be 2000 for you if you are doing something complex. And then it has, because I mentioned that this is the mindset of Raytune development has been across the platforms, across the schedulers. There is an element of cloud nativeness in the whole aspect, and one of the manifestations is sync configuration. So if you are doing something that is local and local to the disk or local to something, and then you want to sync it to something more central, like a S3 bucket or a shared file system that it's writing in local, but it's supposed to go somewhere else as an archive or a repository. That sync function will come in handy. Since we are using a shared file system ab initio, we don't need that. So we're setting it to none. So where does checkpointing help tune? Is it saves intermediate models throughout the training. It uses this to preempt machines by automatically restoring from the last checkpoint. So if you want to resume the experiment from where it broke off, like for example, if your job or jobs hit the wall time, you can start from the last completed experiment. And in some scenarios, the schedulers, I'm talking about the trial schedulers, help get help from the checkpoints. Excuse me. Checkpoints by pausing the trials and then doing some intelligence on the metric, and then maybe copying the model as a checkpoint, which is a better one. So one of the trials was better than the others. At certain sync up fence point, it will try and see, okay, fine, which one is the better one in terms of performance. Let's copy that on all of the resources, and then let's start from there with different parameter values on all of them. See if we can tune that model better. So now there is very clear, tangent in the hyperparameter space where you are actually curtailing quite a lot of space and not going there at all.
Okay. One question. Do we still have the time limiting position to use the GPU? Do you remember what at some point we didn't allow to use certain CPU for more than X amount of hours?
Since A100s, X amount of hours. Since A100s are in the batch queue, the same applies to everything now. Everything is in the batch queue. I'm not sure. Let's ask Greg about that. There is certainly a limit on the number of GPUs per user concurrently using it, and then a number of jobs that a user can submit. But I'm pretty sure from a compute power point of view, nobody's going to hit that part. The whole idea of this is to curtail the number of jobs at the end of the day. Okay. So as I mentioned before, one of the aspects of this is stopping and resuming experiments. So stopping mechanism can actually be implemented as an early stop of a bad trial, right? You can set it so that it can save your compute cost. You can use the pre-existing stopper functions in the tune, or you can write your own, depending on your logic. And you can actually impose that if a trial is performing bad, curtail that, and by setting this flag called fail fast. The resuming part is implying different here. As I mentioned before, if the experiment for some reason crashes, right? You can start from last completed ensemble set. And this is talking about the trials, not the whole batch that was selected. Okay. There is a log of Redis database. So the expectation is there that Ray will not exploit and rerun the hyperparameters it has already used. Okay, so we'll choose furthermore from the space. So there is no repetition of the combination of A and B. For that, you need to set resume equals true. So we'll check that out in this demo, the next demo. Logging and analysis. By default, Ray logs go to home directory. Home directory. It's not a very good place. Some of you have already seen that it is only 200 gigabytes. The naming convention of the directories is the experiment name, Ray results / experiment name / the experiment ID with the parameter values and some timestamp. You can relocate it in using local underscore dir equals that value. And you can add verbosity as well if you wanted to have more information about the trials. You can use a Ray dashboard, or you can log your results in TensorBoard if you are more familiar with the TensorBoard. Okay, so as a second demo, what we'll do is we'll run through the MNIST PyTorch script. This time we'll be using GPUs. We'll be implementing checkpointing and logging and exploring some dashboard. Logging, yes, dashboard, you have seen it already. And elasticity in increasing the resources for ongoing experiment. I think the last bullet I have demonstrated a little bit, but let's try and do it in this demo as well. Right. Okay. Ray head and Ray workers. Of them. Let's clean the logs directory and TB. At the moment, I'm not doing any TensorBoard integration, but you can do it. I mean, it's a general writing and summary and all that that you usually do. And then pass that callback to the tune. So again, there is nothing special happening in the job scripts. They're pretty much the same. But let's look at the, actually, let me see if I can find a better editor to go through the Python script. Okay. Show later. Don't bother me right now. Yes. Right. So here we have that. Okay, is it visible or should I blow it up? Enlarge font? How's that? Okay. All right. The first part is pretty standard. There's nothing special happening here. It's just torch that because I'm using torch. And then the Ray is being loaded. This is my model, as I usually do. You can get it from Torch Vision or somewhere else. This is my training loop. I'm very familiar with it, right? There's nothing special happening here. This is my test loop. And these are my data loaders. So this is pretty much the same thing we do in a usual deep learning script. Okay. Now this is my trainable API. Okay. So here, the trainable API is accepting config, the config dictionary that we saw before. And in addition, I'm also passing the checkpoint directory here. Okay. Use CUDA equals discover if there is a GPU. If there is a GPU, set the device to CUDA. And then run your data loader instantiation. Set the model. Put it on the device. Now, remember, this is what is going to run on every single trial, right? The configuration or in the config dictionary will keep on changing for every trial. So concurrently, 10 trials started with different parameters. We'll say learning rate and momentum, different learning rate. And every single trial is doing the same thing here. Now, we are reading the learning rate from the config dictionary and the momentum from the config dictionary. So exactly, yes. And the optimizer is local to this trial, right? Now we are checking upon the checkpoint directory. If it exists, we are doing checkpointing. If not, well, skip that. If we are doing checkpointing, the checkpointing path, excuse me, is this. We may want to load checkpoint, a pre-existing checkpoint from a pre-existing checkpoint. If we are doing, what is it called? Resume on a trial itself, right? And the dict, I mean, this is boilerplate of DL 101. There is nothing special happening here. And then we get into the epochs. In the epochs, we run the train function, right? The train function was describing the for loop on the batch index, right? The outer loop, the epochs for loop has been implemented in the trainable API. That's the only difference that you have done. Does it make sense? Generally speaking, when you look at your DL script, you have a for loop of epochs, and then within that for loop, you do iteratively the batching. Okay. Here we have just deconstructed that. We have taken the for loop, put this into a training script, training function, and then calling that function every time. That's the only thing that we have done. And then we are collecting a metric of our interest, that is the test metric, the accuracy of the test. And then we are implementing the checkpoint, writing the checkpoint, tosh.save is being used. It's the general thing that we do, and passing the accuracy metric as mean accuracy to our tune.report. That's our collector. This collector is going to link this accuracy metric to our server's journal, where it is going to decide stuff, right? Based on the, and this is equivalent to the score in our objective function. Okay. Here I am defining a custom stopping criterion for an experiment, that if mean accuracy is greater than 0.8, that's a very good trial already. So stop it. Or the training iterations have gone past 6 and the accuracy is still less than 0.5. So that's a bad one, right? So I'm manifesting both good and bad, and then this is my stopping criterion. You can be as complex as you want in this scenario. This is my R parser, the general stuff. This is Pythonic. There's nothing special in there again. I'm calling my array init, and this is my main function, by the way. I'm calling my array init as I was doing before. And here I'm doing the tune.run. This looks really, really familiar. Now there is more than before in this part. That's the trainable API. That's the metric that I am tracing, right? That's the mode of optimization. what kind of optimization I'm doing on the metric. I'm calling the experimenter name so I can identify it. Now I am adding GPUs in the resources. So y number of CPUs and y number of GPUs, right? For every single trial. I'm setting the stopping mechanism to stopper and then putting fail fast in place so that the bad trials are curtailed, so that the stopper is implemented. So even with the same code, if I had fail fast equals false, the stopping mechanism will be disabled and all the trials will run to the end, right? I'm setting this as a Boolean, which will be parsed from command line using the arg parser if I want to resume or not. So I'll demonstrate resumption as well in a second. These are the total number of, excuse me, these are the total number of trials. And these are the maximum concurrent trials that a batch should be running. Rest is the checkpointing. Local directory relocates the logs, and rather than writing on the standard out, the logs are written in a file, so you can trace the file later. If something goes wrong, you can go back to a file and look at it, because this is the concept of batch, right? You need to submit and go home, and then when you come back, you discover. Syncing, we don't need any syncing of any file systems. We want to keep 2 checkpoints maximum with a mean accuracy that is good, to keep the checkpoints to a minimum. Otherwise, if you had 200, you will end up with 200 model checkpoints. We don't want that. We want to keep 2 best ones at any time. Okay. Then at the end, once this is finished, we then print the best configuration. Okay. Let's see if this works. Just before we move on, let's look at the head node. The head node does exactly the same, except you can notice here that I'm not asking for any GPU for a head node or a server node. The reason for that is very, very clear. I don't need the GPU requirement for running a database. It's all CPU work. But I'm adding 4 CPUs for my memory requirement. 2 GB per core is coming with it. I can exclusively add more memory to it too, if that is the case. There's nothing special happening here. It is all the same as before. Here we go. That's the Python script that I'm invoking with all the arg parsers that we had set. And a resume directory is also mentioned here. So minus resume false. If I do that, that would be the first run. I was trying to do the same. Let me check this. What is the no. So what I want to do is I want to get rid of it for now, actually. So the logic is if this exists, this will be considered. Otherwise it won't. So this is the first run. So let me do the first run first. And the worker node remains the same. There is nothing different, except I'm asking for 4 GPUs here. Right? And 16 CPUs. So 4 CPUs for each GPU. Make sense? I should say GPUs per node here. Oh, I'm changing it live. I have already got butterflies in my head. Let's hope everything works. All right, let's batch. See how that goes. Tail on the output. It has started TensorBoard. It has started the array. It's waiting for the workers to start. Workers will start in a bit. There are a few sleep commands in there just to fail safe the things. Yep, it has been submitted. And let's see when the workers connect. So it is one worker at the moment. But as I mentioned before, you can have either multiple workers to start with, like num workers equals blah, and then more workers, or you can add more workers. So now you can see the resources are 4 GPUs and then 17 CPUs. So where is one coming from? One is coming from the server itself. They are putting their contribution in it. The trials are running with some learning rate and some momentum. They're using GPUs. Okay, so we're churning through fairly quickly because these are short trials. You can do more complex stuff if you want within your logic of the training. All right, let it run through. We could submit another one just for the fun. It just increased. It should increase the resources to see 8 GPUs. And here we go. That's 8 GPUs for you. Okay, and the CPUs also increased to 33. 16 plus 16 plus 1. Right? All right, while it is running, any questions so far? And when it finishes, we'll look at the resumption.
Theory, I just need to replace your model by mine.
Yeah. Yeah, indeed. That's the highest level of assumption. And then you go deeper and then the heat hits. So I canceled everything, emulating that basically something has gone wrong. Okay, either the wall time has hit or the machine went down. Hopefully not. Okay, now let's go back to our head node. Okay, I have a script already. It's called resume, and it's doing excuse me, pretty much the same thing except for this. Okay, the anticipation is that I'll start from where I left off. So I'm going to add the head node. And the resources need not to be the same as well. That's the main point, because it is disconnected with the resources. Whatever you throw at me, I'll just start with that. It is up to you to make your deep learning script agnostic of CPUs or GPUs as well, because Ray doesn't do that for you. You discover the device, right? So you should have a logic in it. The second job is 6.1. And if this starts, then we can take a break. And then there is information about checkpointing. So it is reading, and then it is starting from 22nd trial or something like that. Did it say anything about resumption? Oh, I did a, which registry? Which job did I submit? Oh, I submitted the job without resumption. Okay, let me do this again. Let me kill this. Submit the head node resumption. Check resumption is there or not. Just, yeah, it's there. Batch head node resume. Okay, the anticipation is that I'll start. Probably I'll start from 1 anyways in this because I did not let anything finish, but let's see how it goes. Okay. So in resume scenario, the checkpointing does matter. Okay, there were no check. That's okay. None of the experiments finished. That's why it did not find any checkpoint per se. Let's repeat the experiment and let's take a 10-minute break. And I'll probably try and run both of them and then show you both of them in the meantime. Okay. So let's have some coffee and croissants for 10 minutes and we'll start at 10:50. So far, any feedback on the relevance of this? Yes.
Actually, to run like all the experiments with OpenML, it's just typically you implement even single training cycle, it becomes bulky for you. So for me, it's for people, not just training, but tons of analytics.
Yeah.
Dumping the distributions, the statistics, and everything. You can just draft those. It becomes very bulky, and wrapping all this stuff into OpenML is fabulous. So don't get to that stage.
True.
And have the time for wrapping into OpenML.
So one fun part is, indeed, I agree with you in principle that you need the end product of analysis, right? Do you need the end product of analysis for every single, every single experiment? A bad one as well, So that is a consideration.
For example, I don't follow which run several hours. And,
yeah.
Training cycle. So I just leave it overnight. And many was like the new points for the course of days. Every day. But of course, if don't know, it would be way better if I had multiple views.
Yes, indeed, that's the whole idea. To curtail the number of jobs that are in the queue, so that because each trial is a job otherwise. Yeah. So I on Yeah. Okay. Good point. Right. I'll let it finish again. We can get a coffee.
I'd like to ask everyone, did anyone use AutoML practice?
You can use that. Not how to know.
Yeah, so we
Depends on the project.
yeah, we did some training on Kubernetes and Kubeflow especially. And in that, there was a concept of AutoML there in a much more user-friendly manner. It does, if you have good visualization of what's happening in hyperparameter space, it was really intuitive. Let's see if we have any logs. Okay. Okay, checkpoint. I would imagine that there is a checkpoint here then. Okay. So let's see if I can resume. I mean, AWS and Azure are pushing quite a lot by encapsulating it as workflows in their SageMaker, for example. And there is an there's a AutoML implementation in Azure Stack Flow.
Of course, they were able to their proprietary.
Yeah, so essentially what I'm trying to say is they understand, as you just mentioned, that not many people go towards this on their own. So they expose it in their own APIs, in their own programming frameworks.
But if you have like production and those of resources,
Yeah.
You have to fight the problem.
Yeah.
You just need to use 0.1% of accuracy from the credit that you
Possibly.
You would do this.
Yeah.
But when you're in the research stage,
Yeah.
It's really an extra effort to.
This is an interesting observation. From a data scientist, I would accept that from a data scientist perspective. I would really like to understand whether this is the same feeling of a domain scientist as well. So that's what this room does to us. I mean, there are two of the weather scientists sitting here, and you are a computer scientist and AI researcher. This fellow is bioinformatician. That fellow is pure data scientist. And I forgot your specialization again. Climate. So there are three people from climate. So I'm really interested in future to hear from these guys as well. What do they think about hyperparameter tuning per se? If that bit did make a huge difference in the impact of it. Not, it might just be 1%, but holistically speaking, they didn't make an impact. Okay, I think my resumption experiment is taking too long, but take my word, I tested it yesterday. It is going to work, right? So for that to work, some of the experiments need to finish and do the checkpointing. Then you kill it, emulate it, and then basically do the resumption. So the scripts are all there. You can try it on your own. All right. So once we are we understand all the infrastructure, let's get to the search algorithms. Now, these are basically wrappers to third-party open source optimization libraries, Bayesian optimization, HP band, Hyperopt, Optuna, and so on and so forth. The configuration of the search space is the way to expose these search algorithms and the schedulers associated with it. Okay, so if I take the example of Hyperopt library, I look at Hyperopt, how I want to, so I need to have some information about Hyperopt itself, how it does, and then I pass the search algorithm to Tune to use that, right, as an object. It will go in the Hyperopt mode and then do the parameter searching part in Hyperopt mode, and then bring back the end result of that search within the Tune framework again, so that it can be implemented. The scheduler algorithm or scheduling algorithm, the main intent is to fail fast or save on failures. It actually helps schedule trials. The trials can be bad and they can be terminated early. The trials can pause or be cloned, depending on which kind of strategy the search algorithm is trying to use. And alter the hyperparameters as the tuning progresses. So essentially, hyperparameter spaces can ab initio be started in a way, but then can be mutated, right? The space itself can be mutated depending on how the experiment is going. Okay. One of the examples of this is a population-based training. So the approach is just like genetic algorithm, which is a combination of a random search and some hand tuning or manual tuning, as Dimitri was talking about. You can go and look at the parameters and then so on and so forth. But before that, you did a brute force on some parameters. You start with random initial values. Here you have the random initial values on the model. So both models have, they are same models, but with different initial values. That's why the color is different and with different parameters, right? And they will end up with different performances. Okay. So after a certain number of trials, right, there'll be a stage that you can impose. That's a fence, kind of a synchronization fence, which can be called as exploit. In exploit, you coordinate between the trials and revise the baseline model. Okay, you choose the best performing model on that fence between all the trials. Let's say 10 trials ran, and then trial number 6 is the one that is performing best. You copy that model everywhere, and then everyone starts from there, right? And then this is the stage where it starts to explore. So now every trial will have different parameters, but they are starting with a good enough model from there on. So you have a better chance of going in the right direction rather than having other stray trials going elsewhere in the parameter space. Okay. So how it is implemented? Excuse me. For this, periodic checkpointing is mandatory. As you must have seen, that you need to copy the models. You need to define the scheduler. In the scheduler, the attribute of time tracking is important. This should be a metric that is monotonically increasing. Let's say training iterations, for example, or epochs. Granularity of perturbation. So how often do you want to have the exploit done, right? After what intervals do you need to done? The finer granular it is going to be, the more heavy it is going to be on the checkpointing. So more files will be created. Then you can implement a scheme of mutating the hyperparameters themselves. For that, a hyperparameter value can be a list or a tuple or a function even. And the mutation can be either of the two. It can be a linear mutation. So every Y number of trials hit the exploit, and before exploring, multiply every parameter by 0.1 or 2 or 8. That's the default. Or you can put a redistribution of this whole space with a probability of 0.25, right? So that will create a new parameter space from there on. To reconfigure the whole hyperparameter selection itself, to skew it towards a better scenario. Okay, so let's have a look at the script. Actually, I'll use this. This is better. Okay, so this time I'm doing pretty much the same thing, except I am loading the scheduler, population-based training. My training script looks pretty much the same. There's not much changing there. My training API also looks the same, right? And that is a good validation, because if you think about it, the training API is not changing because it is dismantling the two processes. This search and the scheduling of the trials is kept separate than the actual DL training itself. That is important because the decision making of what is the hyperparameter, which is ab initio setting, is happening somewhere else. That's a good thing. I'm still using the stopper condition, and here I am defining a scheduler from the population-based training class with parameters. What am I tracking? Remember the monotonic increase in a metric. I'm tracking training iterations. And on that training iterations, I am setting a fence of exploit every 5 trials. After every 5 trials, do the exploit where you check all the models, see which performs better, and then you copy that model onto all, and then with the new hyperparameters, you start. And what would be the new hyperparameter mutation? I am using mutation of redistributing the random, the learning rate between 0.01 and 1 as a random distribution, uniform distribution. And I'm giving a list this time to momentum. So the momentum can either be 0.8, 0.9, or 0.99, right? When I've done this, now I'm ready to pass this scheduler algorithm to my tune.run, and it will consider that. I've set reuse actors equals true. This is important because I save quite a lot of common denominator in memory, and the memory becomes persistent. So some of the information from previous trials will be kept in memory on the worker node, so that can be reused by the next trials whenever it is possible. I'm setting my resources and then my learning rate and momentum ranges. Oh, sorry. This was the multiplication factor to change the hyperparameter, by the way, 0.8, 0.9, and 0.99. So the first exploit, it will do 0.8. The second exploit, it will mutate to 0.9 times 0.9. And the third one, whatever the value of momentum is from this, will be multiplied by 0.99, right? So I'm setting fail fast. Everything remains the same. Okay, so let's try and run that. Yes. 20 new hyperparameters, but in an intelligent manner that it is skewing towards something good. Refining over refining. Yes. Refinement over, as I mentioned, to some, it may be an overkill to say, okay, I'm getting 0.5% more accuracy. Does it even matter? But to the others, it might just be, you know.
Ranges, they are like hyperparameters that you probably think, oh, hopefully I put the lower bound too high, maybe I give lower. I wouldn't say to the first with zero and such framework exists.
Possibly, yeah. Which basically means your factors will be different accordingly in that. You can go with a, rather than 0.8, you can go with 0.1 to mitigate that parameter at all. Or not consider that parameter, as you said, to zero, set to zero, right? Yeah. Okay. So how are we doing on time? Okay. Head. Hugs. Support. Clean that up. So again, yep. Stay along that. This time we are using PBT as a scheduler, so there'll be some information dumping here. And I think if I'm right, the worker memory will be a little bit higher as well in this scenario. So you need to allocate a little bit more, or expect at least to allocate a bit more. Okay. So the experiment is starting again with 4 GPUs. Okay. Yeah. So it started the PBT and it looked for checkpoints. There is no checkpoint because we are just starting. And it is exploiting and exploring after a certain amount of time. The logs are pretty useful. So it is telling you quite a few things, what it is actually doing. It's cloning the trials. As I mentioned, cloning means just copying stuff, the same model elsewhere as a fence. and then perturbing the model times 0.8, the new LR value, the new momentum value, resample to 0.99. So, okay, so this has finished because we did not do many trials in that. And the value, okay, if I do like, I know that momentum is usually close to 0.9. These samples are pretty small here. If you do quite a few samples, I mean, you will be close to a very, very good value here, at least in the MNIST scenario. But you can always use other simpler schemes like Bayesian optimization. That is fairly common in scenarios, certain scenarios. Okay. So that was just a demo about the schedulers, how to add schedulers. So last thing is, if you want to use a third-party tool like weights and biases, there are others as well, but weights and biases is probably a bit more popular in KAUST. And what is it? It is a repository to archive the experiments hierarchically as organization and in a project. And then there is an experiment in a project, and then the experiment has several trials. You need an account on weights and biases. It's a third-party product and has an API that you can use. You can archive your experiment runs, your model versions, and then your data versions associated with it. The models and the data is not going there. It's just that it snapshots what model and what version, what data version was used. Ray provides integration as a class and as a function decorator to WANT-B. I think, if I'm not wrong, with Ray 2.2, this has been deprecated. It still works because I am using it in the example, but this will go away. The function decorator will go away. So the only thing will be left is going to be the class. The class is a class of a logger, and you can use a callback to that. For those who are familiar with Keras, callbacks are pretty common there. The prerequisite of using WANT-B is that you need to have an API key, which you will generate from your account on WANT-B, and will put it in your home directory, and your WANT-B API that you're calling in your Python script will try to access that and then read that to log you in, basically. On IBEX or on KSL systems, it's not a very good idea to sync with the WANT-B server that is outside very, very frequently. You will kill your job, basically, because you are bringing an intervention of internet in it as you go along. So every trial after it finishes will ping this remote server. Now imagine you are running hundreds of trials, right? This is going to be really, really heavy lifting for the compute node or compute nodes. And someone can flag saying, what exactly are you doing? And if there are many people, I'll be in trouble. So the idea is not to ping or sync in situ, but put everything in the directory. I'll show that to you, and then sync it once, right, as a single job. So I'll show that to you right now. So first, let's have a look at the before. First, let's have a look at the infrastructure. How do you set things? You call upon the integration to call wand_b and import wand_b logger and the wand_b mixin. Wand_b mixin will be used in this script as a decorator. So again, you have your same script as you have been dealing with. There is nothing special happening. And I'll go straight to my trainable function. My trainable function now is decorated with wand_b mixin, and it will bring the boilerplate code on its own. That's an instantiate wand_b basically. And when I'm ready to record the metric, I'm recording metric in two places. One to the tune, as I usually do for decision making. The other one is to the wand_b.log. So it will start logging the score or the metric that I'm going to discover on. The real changes are here. In this scenario, I must name this as an experiment. Okay. The other change that I must do is, where is the project thingy? Here it is. Sorry. In the configure, I need to pass this dictionary of wand_b configuration. And this wand_b configuration has two parameters at the moment. One is where is the API file sitting, and the other is the remote server, what project should I put the stuff in? So remember the hierarchy, there's an organization, the API key makes sure that you have access to that organization, right? Once you are in that organization, which project should you add your experiment in? Once you add that experiment, the trials go in that experiment, okay? There are other fields as well if you want to populate, but they are usually optional for me at least. So those were the two things that were important. Let's have a look at this head node script. Again, nothing special is happening here, except I am sourcing a wand_b setup script. What does a setup script do? Let's have a look at that here. It has 4 simple lines. The first one it does is it sets wand_b to offline, which basically mean do not sync it to the wand_b server at all. I'm going to do it myself, right? The second one is, okay, you are going to do it yourself. Where should I put the wand_b runs, the data? So you give the directory, and then you create that directory, and then you call this with a wand_b ID. How does wand_b recognize this particular run that you are running, right? So once you have done that, so one other thing that I had done here is I was calling the experiment as exp underscore my job ID, okay? This same thing needs to happen on the worker node as well. So I'm sourcing my wand_b setup script here too. That's the only difference that I have done or made. Actually, the last bits of head node slurm is doing some extra stuff. Once the trial is finished, the experiment is finished, okay, I am adding these lines to sync at the end of the trial. So I'm bringing wand_b online first, then I'm going in the wand_b directory, and then I'm issuing the command of won't sync, include all the offline files that you have created and sync them all. And this will put it into won't dashboard. So let me go to my won't server or instance. This is how it looks like. You need an account. You can have a free account. I use my Google account. And there I have a team. And in the team, I have my profile associated with that team. And then I can create projects, right? If I go to my settings, I can create API keys for different machines, right? I can use one for Shaheen, one for Ibex, one for my laptop, and so on and so forth. This is the recognition of the machines. Wherever that file is, and with this information will be used. So one thing that I need to do is this is supposed to be done only once. So consider you have put your API key here in your home directory. What you must do is with your won't installation, you need to log in. Okay, so this is like authentication of your key to your remote server. This is supposed to be done just once. Okay, I already have logged in. So the login will do something interesting. It will create another file. It's called netrc file and will put some information in there as a second hash. All right. So I'll leave those steps there. They are pretty common steps. When you look at won't these are the first things that it talks about. Once you have done that, now you can submit your head node script. Stay on it. Sorry, 3, 5, 8, 5, 3, 5. Okay, let's see. Yeah.
On the new weights and prices, also think that also now functionality apart from coding by experience.
I am not familiar whether it can back integrate into Tune. For that, you need persistence. Right, I'm using it as offline. It's telling me that it's going to record everything into a directory. So I need to basically do a post step of syncing everything back to the remote server. Yeah.
This is across parameters now dynamically added to dashboard.
Okay.
Remember this
Yeah.
visualization though.
Yeah.
Parameters.
Yeah.
Can you see during
No, so I've switched that off. I've switched the syncing off. So there's no data on the remote side at the moment, right? But the last lines are going to do exactly that. They're going to push all the data now to won't and then I can see it. I'm not a won't expert at all. So I won't really understand what all the data is supposed to be meaning there. So this is what exactly it's doing right now. It is dumping everything or syncing everything to 1B. This is an expense. This can be an expensive process. So decide yourself whether you want to do it within the job script or as a separate thing, right? Compute nodes are internet bandwidth limited, by the way. So if this is like hundreds of files, try do it on data mover node or somewhere else. Okay. Those were the few experiments it has pushed.
Why it takes so much time to upload? It's just several numbers.
Yeah, these are several files actually.
What's there the files?
I think there is a lot of metadata. If I go back to my finished 32 seconds ago and then click on a trial, for example, yeah, there is quite a lot of metadata in there. I think you can curtail the metadata as well. But when you look at the metadata, it actually has quite a lot of information. The GPU temperatures and all those things, there's a humongous amount. You can curtail a lot of stuff in there. I just did a vanilla implementation just to show that there is an integration there. So that, and let me go back to, yes, I was, here we go. Yeah, here we go. Come on. It shouldn't be thinking that much. I think there's something. Oh, it's still syncing, I think. Connectivity outside, yeah. So yeah, this is the agglomerated version. And then you can go to a single trial and then look at these. I mean, they're not as pretty as you would expect it to be. I'm sure that an expert would do much better. But as I mentioned before, this is the excessive information it is giving. It's just a single data point, but it is a data point wrapped in, and then it has to be pushed out. So I would say, yeah. So I think we did a few trials. These are the runs. Yep. So I can see around 22 trials here in total. It is adding to the same group. I ran it before, so it has added some more trials to the same group. So again, don't ask me what exactly that means because I'm not a big user of 1B. Is anyone here a weights and biases user? I think one of them was there, he left. Have you used weight and biases before, Dimitri? Again, there's a lot of documentation. So if you want to use weights and biases, you can actually do it. Okay. All right. That's a very important question, actually. I don't think that the data is going. The metadata is going for that data. Yeah, has footprint in it. Yeah, yeah, yeah. The environment is going. I'm sure of it. The Conda environment is being captured.
It does have an option to actually install your own server.
That's true. I'm not sure that how many Yeah, you have to have a justification of 10 to 15 people at least to do that. And it's not going to be on Ibex or Shaheen or us. IT will do it, if at all. It is.
Then Microsoft will buy it.
And they will, yeah, that's how it works, right? Yeah. All right. So I think that brings me to the end of my spiel. Yeah. So conclusively, I mean, I'm going to say that it's a backend that is supported by community and enterprise. So the company's name is Anyscale, and they are doing quite a lot. Ray is doing quite a lot than just Tune. And they are into enterprise, so they are going to stick around for quite a while. Ray in general has strong cloud integration, integrates with all major cloud vendors, so they have their own recipes. S3 backend is also supported, both for cloud and for on-prem, supports Kubernetes and containers. So that's also a strong point of Ray in general. And KSL support for Ray is going to be dependent on you. If you like it, if you are going to run with it, we are going to support more of it in terms of documentation, experimentation, and so on. All right. So yeah, any questions, comments, feedback? And I'll say goodbye.